The Banach Contraction Theorem, or the fixed point theorem, Banach fixed point theorem, appeared the first time in 1922. It's an old theorem that has been known before in different forms, but the actual form that we teach in any function analysis course is the one that is known as the Banach Contraction Principle, and as I said, it appeared in 1922, published by Banach. So in order for us to set the stage, let us start first by some basic definitions. So we take let MD be a metric space, and let's take a map. Let T be a function defined on M. We'll say that T is a contraction, if and only if there exists K, a constant between 0 and 1, such that the distance from Tx to Ty is less than K times the distance from x to y for any x and y in M. In other words, that the map T shrinks uniformly the distance between any 2 points in M. If you take x and y in M and you look at their images Tx, Ty, the distance between Tx and Ty is smaller than the distance between x and y. So some of the basic properties of such a map. Okay, so first of all, what is a fixed point? So a point x in M is called a fixed point of T if and only if T of x is equal to x. Okay, so the if we look at T as an input-output relationship, then in this case a fixed point is just a point where the input and the output are identical. Okay, so what's interesting is that many functional equations, or algebraic equations in fact, the roots or the solutions can be seen as a fixed point of a map, okay, or a function. And that's why it's one very powerful tool to allow us to see under what conditions such map T has a fixed point. So let us, in this case, note that, first of all, okay, from the definition of T, okay, if x and y are fixed points of T, then we have d of x, y equal the distance from Tx to y, because Tx equal to x and Ty is equal to y, and because T is a contraction, it's less than certain constant K that depends on T times the distance from x to y. And since K is less than 1, since K is less than 1, then we must have the distance from x to y equals 0, or x equal y. So what does it mean this? It means that T has at most one fixed point. It can't have more than one fixed point. Okay? Number one. Number two, okay, we also have the distance from Tn of x, Tn of y less or equal than k to the power n distance from x to y. Okay, keep in mind that Tn of x is just the iteration of t. Okay, so we take t of t of t of t n times of x. So if we keep using the definition of T as a contraction, k times, n times, we'll get k to the power n times distance of x and y. This is true for every x and y in M, for any x and y in M. So in particular, we have the distance from Tn of x, Tn plus 1 of x, less than the distance from x to y. I'm sorry, from x to tx. Okay, so in particular, we get that the series, the distance from Tn x, Tn plus 1 x is convergent from 1 to infinity. Okay, which implies that the sequence Tnx is Cauchy. Indeed, okay, for any n greater than 1 and h greater than 0, we have the distance from Tn plus h of x, Tn of x less or equal than the sigma of Tn plus k plus 1 of x, Tn plus k of x. K goes, I'm sorry, not k, because we already used k, so we need to remove k. So we need to use a different symbol. So let's use I. I from I equals 0 to h minus 1, which is less than sigma I equals 0, h minus 1, k to the power n plus I, the distance from tx to x, okay, which is equal k to the power n, 1 minus k to the power h over 1 minus k, distance from x to tx, which implies, okay, that the distance from t of n plus h of x, t of x, is less than k to the power n, 1 minus k, the distance from x to tx. Okay? If we let, so this clearly proves that our sequence is Cauchy. So here, clearly, since k to the power n goes, since k to n converges to 0, this is a sequence of real numbers, k is less than 1, converges to 0, we get, oh, I'm sorry, there was a mistake here, there is an n missing. We get, again, Tn of x is a Cauchy sequence. Since now we use completeness, since M is complete, then limit of Tn of x, when n goes to infinity, exists, and it is a point in M. Now, let us prove that z, in fact, is a fixed point of t. Okay. So what do we have? First, we know from the following inequality, this inequality here, So this inequality here, not this one, sorry, not this one. Let's go up, up, this one. This one. This inequality here, okay, tells us what? That if we let h go, this h here, go to infinity, okay, we get, okay, the distance from z to Tn of x is less or equal k to the power n 1 minus k, the distance from x to tx. Moreover, okay, we have the distance from Tn plus 1 of x to t of z is less or equal than k d of z Tn x. Okay, so if we let n go to infinity, then we have, okay, we have limit of the distance of Tn plus 1 x t of z equals 0 when n goes to infinity. Okay, and since Tn plus 1 of x also goes to z, the uniqueness of the limit, the uniqueness of the limit gives z equal t of z. So z is a fixed point. So what are the, and we know from previously, we have seen that t cannot have more than one fixed point. Okay, so this tells us what? That for any x in M, okay, the limit of Tn of x is the only fixed point of t, and is independent of x, the starting point of the iteration. So putting all these results together, we get the following theorem, which is the Banach Contraction Theorem. This is the classical Banach Contraction Theorem. It says, let M be a complete metric space. Let T be a contraction. Let K be less than 1, such that the distance from Tx to Ty is less than K, the distance from x to y, for any x and y in M. So such K exists because T is a contraction. Then, this is the conclusion of the Banach contraction. Then, number 1, T has a unique fixed point z in M. Okay, keep in mind this means that dz equals z. 2, for any x in M, the sequence of iterates, Tn of x converges to z. Moreover, we have the distance from Tn x to z is less than k to the n 1 minus k, the distance from x to tx. So, in other words, you have an existence, there exists a fixed point. You have uniqueness, it's unique. And not only that, this theorem is so powerful because it gives us, in fact, it gives us a kind of approximation of the fixed point. So this property here is the box formula here is so powerful because it tells us that we can approximate the fixed point z by the iterates, and the error by taking the error is less. In other words, remark. Okay, so by taking, if we take Tnx for the fixed point z, we commit an error. So the error is, by doing this, the error is equal to the distance from Tnx to z, but we don't know the fixed point, and therefore we don't know the error, but we know that it's going to be less than kn over 1 minus k x tx. So we know k from t, okay, and we know n, and we know again the point x and tx. Therefore, we know an upper bound of the error. So it tells you how close you are to the fixed point. So it's a very powerful result. It's not just that you do have a fixed point, but there is a way of approximating this fixed point. So if you don't know it, you can use the iteration of any point, any starting point, and get the fixed point. It's really beautiful. Let me just give an example, okay, a nice example to illustrate the use of this theorem. So let's take the function f from 0, 1 into r, okay, with f of x equal x cubed plus x minus 1. So we can graph the function and see that in fact there is only one point where f of x equals 0, or f of x crosses the x-axis. In other words, root of f of x. So this equation, f of x equals 0, has a unique solution. Okay, but this is a cubic equation. It's very hard to solve. Is there any way we can approximate it? So first of all, note that, okay, f of 0 equal minus 1. F of 1 equal 1. And f prime of x is equal to 3x squared plus 1, which implies f prime of x between 1 and 4. Now, set g of x to be equal to x minus 1/4 f of x. Then g prime of x is equal to 1 minus 1/4 f prime of x, which implies g prime of x between 0 and 1 minus 1/4 equal 3/4. Great. Now, g of 0, so g is going to be increasing, but g of 0 is going to be equal to minus f of 0 over 4, because it's minus 1, f of 0 is minus 1, so it's going to be 1/4. and g of 1 is equal to 1 minus 1/4, which is 3/4. So g, in fact, goes from 0, 1 inside 1/4, 3/4, which is a subset of 0, 1. Okay, so g goes from 0, 1 into 0, 1. So 0, 1 is a closed subset of R, which is complete. Therefore, 0, 1 is complete. In fact, it's even compact. And if we use the mean value theorem, okay, we get that g of x minus g of y, absolute value, equal g prime of some point a, x minus y, where a is between x and y, which is equal absolute value of g prime of a, absolute value of x minus y, less or equal 3/4 x minus y. So g of x, g is a contraction. So g from the Banach Contraction Principle has a unique fixed point in 0, 1. Great. Note that g of x equal x if and only if f of x equals 0. So this root of f of x that we talked about, the unique root, can now be approximated by using the previous theorem as the iterates of any point between 0 and 1. So in particular, g of 1/2, the iterates of g at 1/2 converges to the root of f of x equal 0, the one that we're looking for. Okay, and we know that if we write denote by z, that root, unique root, okay, then we have, okay, g, the distance, gn of 1/2 minus z, absolute value, is less than 3/4 to the power n, 1 minus 3/4, and g of 1/2 minus 1/2. Once all calculations are done, we get g, the iterates of 1/2, minus z, less or equal 3/8, 3/4 to the power n, which is equal to 1/2, 3/4 n plus 1. So the error by taking the iterates of g to the 1/2, the iterates of g, the nth iterates of g at 1/2. So this gives the error when we approximate the root z by the nth iterates of g at 1/2. So one can easily plug in these numbers and come up with some approximations, and this quantity here gives you how close you are to the root of that equation. Before I close this, I would like to mention something about people for the last almost 100 years or 80 years have been working extensively of extending this Banach contraction theorem. And the best approximation, I'm sorry, the best extension is the one done by Caristi around 1975. And the way he did it, he went back to this the proof of the Banach contraction principle, and he looked for a different proof, and he came up with the following. So let me show you what he did, the ideas of Caristi. Okay, so let T goes from M into M be a contraction. So there exists K less than 1 such that the distance from Tx to Ty is less or equal than K, the distance from X to Y. Okay, for any X and Y in M. In particular, we have the distance from X to Tx, Tx to T squared X is less than K, the distance from X to Tx. So what he did, very simple steps, but of course these simple steps led him to discover a major theorem, beautiful theorem. So if we go and we add xtx to both sides, plus k, the distance from x to tx. Then he moved this term to this side and this term to this side, and he found that the distance from x to tx minus k, the distance from x to tx, is less than the distance from x to tx minus the distance from tx to t squared x. Okay, so, or 1 minus k, the distance from x to tx is less than the distance from x to tx minus the distance from tx t squared x, which implies that the distance by dividing by 1 minus k, keeping in mind that k is less than 1, is less than 1 over 1 minus k, the distance from x to tx, minus 1 over 1 minus k, the distance from tx to t squared x. So if we set phi of x to be 1 over 1 minus k, the distance from x to tx, we get the distance from x to tx is less than phi of x minus phi of tx. So this is truly amazing. First of all, let me say something. So if t is a contraction, one can find the function phi defined on m into the positive numbers, and such that the distance from x to tx is less than phi of x minus phi of tx. Okay. Clearly, if you take the identity map, okay, so note, okay, if we take I, okay, which is defined from m into m, the identity map such that I of x equal x for any x in m, then this formula here, okay, is satisfied by I. This here is satisfied by I indeed, because the distance from x to ix is 0, and phi of x minus phi of I of x is also 0. So it's satisfied. So the family of maps which satisfies this box inequality for any phi is bigger than the contractions. Okay? So in other words, you have this identity map which is not a contraction because everything is fixed by this contraction. So this family is larger. And what's the question that Caristi asked was, under what assumptions on phi, under what assumptions on M, a map which satisfies this box formula has a fixed point? And he came up with the following. The theorem I'm going to be citing right now is a little bit stronger than the real Caristi fixed point theorem, but it captures the essence of Caristi. So he proved the following theorem. This is Caristi's theorem. Beautiful extension. Let M be complete metric space. Let phi goes from M into the positive numbers. Be continuous. Okay. Let T be a map, self-map of M, such that the distance from x to tx is less than phi of x minus phi of tx. Then T has a fixed point. Note that the fixed point is not unique. So we lost unicity, or the uniqueness of the fixed point in the Banach Contraction Principle. Okay? Number one. Number two, the iterates of T are still behaves nicely, but they will not lead to a fixed point. They don't have the iterates which converges to a fixed point. So the proof of this theorem is a little bit more complicated than the proof of the Banach Contraction Principle. And also we lost, of course, the error, the approximation, and so on and so forth. I hope you enjoyed this lecture, and thank you very much.